Hey everyone, this video is just some extra substitution practice. Section 5.5 can be a little tricky, and when you're first learning these substitutions, there's a lot of different variations, so I just wanted to give you some more examples of how to do it. This first problem I'm going to work out completely, but after this I'm just going to set up the problems with the U substitution, just so you can get some more practice on kind of seeing the big picture, seeing what your U should be, and how to find your DU and so on. To begin our substitution, keep in mind you want to pick the U as the thing that's in the complicated place. It's either inside another function, under a square root, in the denominator, something like that. In this case, we have a function inside our cosine function. So we're going to let this be our U. The other thing you want to check is if you pick something as a U, the du, or the derivative of that, should show up in the problem. Notice the derivative of 4x squared plus 3 is 8x, and that shows up in the problem, so we're going to go for it. Let's let our U be the 4x squared plus 3. And then our du will be 8x dx. And our integral will now become cosine of u du. Right, because cosine of 4x squared plus 3, that was our u, so that becomes cosine of u. And then the 8x dx, that piece is equal to du, so du takes care of that. So everything up here with an x is now translated in terms of u's. This is a simple thing to integrate now because we know the antiderivative of cosine of u would be sine of u. Don't forget your plus c. And then translate this back into x's. We have sine of, remember u was 4x squared plus 3 and plus c. And that should be our answer. So remember, for the rest of these, we're just going to set these up. We're going to translate it into a U problem, and then that'll be up to you to finish off the problem. So we're just going to start the setup, which is the hardest part. So we're going to pick our U as the thing in the complicated place, which is under the square root. So if we pick 3x squared plus x as our U, notice our du will be the derivative of that, right? 6x plus 1. So U will be 3x squared plus x, and then our du, which is this piece, will be the derivative of 3x squared plus x, which is 6x plus 1, and then we get a dx every time you take the derivative of the u part. So that is that. Here is our u, right? So when we rewrite this now, we will have the integral of the square root of u du. So again, this was the square root of our u inside, so that's that piece. And then the 6x plus 1 and the dx, all of that equals du. So the du takes care of that. And now you're just integrating the square root of u, which is the same thing as u to the 1/2, which you can finish off pretty easily with a power rule. We're going to pick our u as the thing in the exponent. We can deal with just e to the x, but e to the x squared is a little bit more complicated, so we're going to let u be x squared. Notice the derivative of that is 2x, and we do have an x. We don't have the 2, but we can adjust for that. So let's go ahead and start by letting our u be x squared, and then the du will be 2x dx. Now again, we don't have the 2 there, we do have the x dx, so let's get rid of the 2 by dividing du by 2, or multiplying by 1/2. That gives us x dx. So now we can rewrite the integral. We're going to have e to the u, which takes care of the e to the x squared, and then for the 1/2 du, I'm going to pull the 1/2 out front, and then I'm just going to write du. Now you can see the, like we said, the e to the x squared, that becomes our e to the u, because u is equal to x squared. The x dx, right, we solved for that, and that was du over 2. So I took the over 2 part, the 1/2, pulled it out front, and then our du is right there. And now you're just integrating e to the u, which is pretty simple. Here, this one's pretty scary looking, but if you notice, if you pick u as the thing that's in the complicated place, right, this is being raised to the 4th power. If u is this, then the 1 doesn't matter. Du would be the derivative of square root of x, which is actually 1 over 2 root x. So if we just let u be the thing inside the parentheses, root x plus 1, then our du becomes 1 over 2 root x dx. If you want to see why that is, just write x as the power, square root of x is the power x to the 1/2, and you should get 1/2 x to the negative 1/2, and x to the negative 1/2 is the same thing as x in the square root in the denominator. So that checks out, and if you notice, this piece is u, so we get u to the fourth. And the 2 root x dx, since this is in the denominator, this is actually the same thing as this. So this should be a perfect substitution. We can write it as u to the fourth, and then just du, which is surprising that it gets so simple after you make the substitution. Let's double check here. Here's our u, root x plus 1. There's our u, so u to the fourth, there's that piece. Now all the rest, picture like your invisible one here. This is 1 over 2 root x dx. That's exactly what our du was. And so this whole piece, the 1 over 2 root x dx, just becomes du. Now you're taking the antiderivative of this, which again, very easy. This problem is a little bit tricky because it looks a lot like tangent inverse, which is 1 over 1 plus x squared, but it has that 4 there, which we could probably deal with it without a u substitution, but just to make sure you get the right constant adjustment, it's usually good to make a u substitution. The first thing I would say is let's think of this as dx over 1 plus 2x squared, right? Because we have that that extra 4x squared, we can think of that as one thing squared, which is 2x squared. And then that will be our u. Our u will be 2x. And then the derivative of that will be 2 dx. We only have a dx, so we can get rid of the 2 by dividing by 2. And then we can rewrite our antiderivative like this. Now the du over 2, I'll pull that 1/2 out front. We'll have du over 1 plus u squared. And now that is exactly the tangent inverse of u with the 1/2 out front, and then you can substitute back in for your u's. So when you have something that's almost like a inverse trig problem or an inverse trig derivative like we had, try to make it look as much like the actual formula as you can, and usually you'll do the adjustment for the constant along the way. So you can kind of do this with the guess and check, but I like to be kind of a little bit more exact and do the subs like that. Here's another problem that looks really scary, but actually once you do the u substitution and you realize what it should be, it's actually pretty simple. If you notice, the top is actually the derivative of the bottom, right? If you take the derivative of e to the x, you get e to the x. If you take the derivative of e to the minus x, you get e to the minus x, but then by the chain rule, the derivative of minus x, which is a minus. So if we just let our u be the bottom, e to the x plus e to the minus x, then the derivative of that is e to the x minus e to the minus x dx. So we can actually rewrite this as 1 over u du. Right? 1 over u, this is the u right here, right? It's our e to the x plus e to the minus x. It's in the denominator, so it stays there. And then the e to the x minus e to the minus x dx, that's all in the numerator here. So I just split it out, but you could actually look at this as du over u, because the du is basically on the top. It's all that. It takes care of this whole piece right here. That's the du. Now don't overthink this one. The antiderivative of 1 over u would be natural log of absolute value of 1 over u. Do your back substitution, get your answer. This last one here is a little bit tricky because it's not your standard u substitution, because your instincts are probably make u 2x plus 1, which is good, but the du of that would just be 2, and we actually have another x on the outside. So what we're going to have to do is make a u substitution and then manipulate our u substitution to get an expression just for x. So let's try it by doing what we said. Let u be 2x plus 1. Du would be 2 dx. Notice we don't even have a 2, so let's just get rid of that right now. Du over 2 would be dx. So that takes care of everything but the x out front. Now if we take our u substitution though, this one right here, u equals 2x plus 1, we can solve that for x. We could subtract the 1 over and get u minus 1 equals 2x. And then we could divide by 2 and we could say u minus 1 over 2 equals x. So now we're going to rewrite this integral in terms of u. And the first thing is we have the integral of x, and our x is this u minus 1 over 2. I'm going to pull out the 1/2, which will deal with the over 2 part, and then we'll have the integral of, try that again, integral of, and this will be u minus 1. So that right there so far is the u minus 1 over 2 from the x that we had. Then we have the cube root of, and this will just be u, and then du. Let's separate this a little bit real quick. Okay, let's take a look at this. So the first part was the integral of x, and we solved for x, and we got the x was u minus 1 over 2. Here's the 1/2, that's the over 2 part, and there's the u minus 1. So together, that makes up the x. Then we had cube root of this, but this is our u, right? So this whole piece here becomes cube root of u, which is right there. And then the dx, we solved for dx and we got du over 2. Remember our over 2, we actually didn't account for that. So we actually need another over 2 up front. It's good that I saw that. So times another 1 over 2. Okay, so now one of these, the 1 over 2 u minus 1, that was this piece, that was just the x. But then when we solve for dx, we also got a du over 2. So this dx becomes du over 2. Usually when I have like constants or fractions like this floating around, try to pull them out front. Remember, you can always factor constants out that are being multiplied all the way out front. And so now, here's your next step. I'm not going to finish it, but we could call this 1/4 the integral. Now if you think of this u right here, this is u to the 1/3. And we can actually take that and then distribute it in here. So first we'll have u to the 1/3 times u. That will give us u to the 4/3. When you multiply, you add the exponents, so 1 plus 1/3 is 4/3, minus, and then we'll have u to the 1/3 again, because we're multiplying it by 1, du. And this is really simple to do because now it's powers. So you can do the power rule for each piece separately, adjust your constants, multiply the 1/4 back in, and then remember at the very end, resubstitute back in for your u. So that's it for this video. Let me know if you have any questions, and hopefully this gave you some good practice on u substitutions.